The heading is Continuous Spectrum, Discontinuous Spectra, and I'm referring to the absorption and emission spectra when I say discontinuous spectra. Right, so we're starting the note when white light is diffracted through a prism, a continuous spectrum a continuous spectrum of all the wavelengths of visible light, a continuous spectrum of all the wavelengths of visible light are seen. They appear as bands of light first up, they appear as bands of light. So if you look to your continuous spectrum, the colors overlap, and this is what we call bands of light versus lines or spectral lines. So I'll explain what that means when I talk about now the discontinuous spectrum. Right, so I'm going to continue by talking about a line spectrum. Right, so a line spectrum appears as spectral lines and not bands of color. Right? A line spectrum appears as spectral lines and not bands of color. These spectral lines correspond to specific wavelengths Alright, so I'll leave it as that. These spectral lines correspond to specific wavelengths, and I'll explain what the lines represent with regards to absorption and emission spectrum. So we're saying we have spectral lines that correspond to specific wavelengths. Right, these discontinuous spectra can be one, absorption. I'm going to use back the word spectrum here. Right, so absorption spectrum, or two, emission spectrum. So I'll go back up and change a word here. right? So these discontinuous, right, so I'll use a word here, can be either, right, so just fixing the English here, can be either a or an absorption spectra or emission spectra. Right, so they both show spectral lines, but what the lines represent differ for each type of spectrum. Right, so we're gonna, in my notes, explain what it looks like and what is the significance. So we have absorption spectrum, and in the absorption spectrum, we're gonna see what do you say? Black lines on a colored background. Right, and the lines are the spectral lines, right, and each line is a specific wavelength of electromagnetic radiation. So each line is a specific wavelength of electromagnetic radiation absorbed by, we could say, an atom or atoms here, right? So, or it can be an element we're referring to. So I'm just going to say by atoms and keep it simple. So it can be atoms, element, whatever. And for our emission spectra, it's going to be the opposite of what we see here. And emission spectra show colored lines on a black background. Where each line, right, is a specific wavelength. So just put this here, specific wavelength of electromagnetic radiation emitted by atoms. Right, so I want to talk about this absorption and emission in relation to the quantum theory. So we can have absorption, which will cause electrons to go from a lower to a higher energy level within the atom. So we'd record for the absorption spectra the wavelengths of electromagnetic radiation absorbed. And for emission spectra, we obtain emission spectra from heating the element, right, or heating the substance, whatever you want to call it. So through heating the substance, it will cause electrons to go from a lower to a higher energy level. But when they drop back down, whatever radiation they emit, that is recorded as an emission spectrum. We are looking at the hydrogen spectrum. So this is the two atomic spectra which is formed by the element hydrogen. Right, we have two atomic line spectra. So I'm going to specify that these are our two atomic line spectra. Right, one is the emission spectrum, one is the absorption spectrum. So let's say we have an element and we heat up that element, or we supply some sort of thermal energy, right? The energy that we supply, right? Let's say we have an electron in a lower energy level, right? Or an electron in its ground state. That's E1. that electron will absorb energy and it will be promoted to a higher energy level. Let's call this E2. So this is one transition here, or one electron transition, and the wavelength of electromagnetic radiation absorbed will be recorded as a spectral line in the atomic line spectrum, right? Also remember that if we are supplying our element with heat energy, thermal energy, electromagnetic radiation, this electron will not just go to one higher energy level, it can go to even higher energy levels. So I'm going to call these 3, 4, 5, etc. Now I want you to understand we're looking at the hydrogen spectrum, meaning we have one electron in the first shell outside of the nucleus. This idea of an electron shell, remember it's theoretical, it's not like a physical space. The electron shell represents where you're most likely going to find your electrons in three-dimensional space. So if we supply an electron with energy, right, it can go to a second energy level, third energy level, fourth, fifth. These are all theoretical, and what they represent are fixed distances from the nucleus. So really we can show in an absorption spectra how an electron can jump from one level to the next, right? And these are all, let's say, theoretical levels. It may be an actual level in other elements, right? But for our purposes, we're going to treat it as if the electron can jump from its ground state, and I'm just going to call the others higher energy levels, right? These are what we call our higher energy levels. Now, every time the electron jumps, it is going to absorb electromagnetic radiation, which appears as lines in either the absorption or emission spectra. Now we're talking about the electron absorbing energy, which causes jumps to higher energy levels. I've mentioned before that an electron in a higher energy level is said to be excited or unstable. So there's two ways to record spectral lines, either as absorption or emission. So in the absorption spectra, we would have recorded the wavelengths absorbed by the atom, and in emission spectra, the same hydrogen that we have heated, instead of recording what was absorbed, we are recording the energy which is emitted as the electron drops back down from its higher energy level to its ground state. So the value for this quantum of energy should be the same whether the electron jumps from lower to higher or from higher to lower once it's the same level. And that is why you're going to see the spectral lines corresponded to the same wavelength in both the emission and absorption spectra. Right, so I just want to expand my diagram a little bit here to show the possible jumps that may occur in hydrogen. But before I do, let us take note of both spectra, and what we're taking note of here is the spaces between the lines. Right, so we're going to take note here, and I'm going to use a term, it's called convergence. And I'm going to explain what convergence is and that you should be able to identify it. So convergence happens, and I can't write here, but let's see, here we go. All right, so it's here or here. All right, this is what we call convergence. And convergence shows the spectral lines spectral lines get closer together, right? As the frequency or wavelength, well, as frequency increases, or I should say as wavelength decreases. And I'll explain what that means. So in any spectrum of any element, but we're only looking at hydrogen, the lines get closer as, let's say, the wavelength decreases. Remember, the shorter the wave, the more energy being supplied or used, right? So this wavelength or shorter wavelength means that it should represent a larger jump, right? That means if we have an electron in its ground state, it would have either gone up to even higher levels in the absorption spectra or drop back down from even higher levels back down to its ground state. So both the emission and absorption spectra, which show this convergence, what the data, which is the hydrogen emission and absorption spectra, provide evidence for is that the higher energy levels are becoming closer together, right? So this diagram, which is our atomic line spectra, can be translated or used to work out the fixed distances of the electron shells away from the nucleus. On the screen, we're going to see an image. I just spoke about convergence, where in the atomic spectra, we're going to see convergence of the lines. And this is as the frequency increases or as the wavelength increases. Now, atomic line spectra have been used to work out these two different diagrams we see on the screen, where based on the atomic line spectra, right, so Bohr in his experiments, he was able to determine that within the atom there were energy levels, and this is based on the lines from the atomic line spectra. So what he came up with is this diagram here called an energy level diagram. The energy level diagram shows the different levels within the atom, where, as we can see, we have our first level, right, which is our n is equal to 1 state. If we have an electron which originally belonged to the n is equal to 2 level, that's the second shell, this electron on absorption of energy can jump to higher energy levels, 3, 4, 5, etc. Right? So the lines were originally seen in the line spectra. It was translated into an energy level diagram. And this energy level diagram can also be used to draw a diagrammatic representation of what the energy levels in an atom looks like, where we can see that the higher energy levels are closer together, right? Or as the energy levels, or as you go higher in terms of the energy levels, they get closer together. So there's not fixed distances between the levels, and this is because of the fact that the electron or the quantum of energy required for a jump is going to differ depending on how far away the electron has to jump. Right, so essentially what we're coming to is that Bohr, from his atomic spectra data, he was able to determine that discrete energy levels existed within the atom, right? And because of his evidence or data which shows quanta of energy, so quantum of energy between the levels, I'm going to just draw it in. So quantum of energy could be change in E, or 2 times, 3 times, whatever. This change in quantum of energy or the evidence, which is the quantum of energy, gave or resulted in the idea of energy levels within the atom.